All right, so this chapter here is more about exponential and logarithmic function. I know you guys have been looking forward to this, right? And this is what we were saying earlier on, even though we're doing exponential and logarithmic function, we're going to come to the point where we're going to have to take derivatives of these functions. But this first section here, 2.1, is basically just a review of the exponential and the logarithmic function that you should have covered in college algebra. So let's just review exponential functions first. Now, what's the difference between a polynomial function and exponential function? Now, if you look at a polynomial function we have here at the very top, the format of a polynomial function is when the base, is a variable and our exponent or the power is a number. So that's the format of our polynomial function. For example, this could be f of x is equal to 5x to the fourth minus 3x squared, whatever. All right, so the base is going to be a variable and the exponent is going to be a number. The exponential function is a reverse of that. In the base, we have the constant or the number, right? And this constant a right here, with our base, is going to be positive and it's not going to be equal to 1. And you'll notice that now the power is our variable. So we've switched roles in terms of the polynomial and the exponential function. So now the base is the number and the power is the variable. So let's just talk about this basic exponential function. One of the more common base that we use is the letter E. Has anyone ever seen E before in math? Do we know what it represents? What number is E? 10? No. You're on the right track. It's not 10 though. 10 is log base, just regular logs, when the base is 10. This is a natural log when we have E. If you take out your calculator and you type in E to the 1 power, what do you get? No, Alfred. And how do we get this E that we're talking about? Some of your calculators are built in E. Well, for most, 2.6, I think it's something like 2.6 or 2.7 something. 2.7, right? So if you type in E to the 1 like this, so E is actually 2.7. I think it was 1, 3, and it goes on forever, ever, 1, 8. There you go. So this is what E represents. So here's our exponential function because E is just a positive number not equal to 1. So this fulfills the conditions of what we're discussing. Now, one of the things we want to look at for these exponential functions is the graphs. open them because you do have a couple of questions in my MATLAB on graph and exponential function. So the basic exponential function has a graph that looks like this. Have you guys seen that before? So this would be your e to the x graph. There's a special name for our exponential function that looks like this. Anyone remembers? No, I'm sure most of you took college algebra in the fall, right? This is called exponential. You probably know what I'm talking about. All right, that's a G.
Exponential growth.
Growth. All right, so it's exponential growth. When it looks like that, it's exponential growth. And what's our y-intercept on this? This point here.
1.
1, right? So this is 0, 1. Now, Samira, you mentioned exponential decay. So exponential decay is when it goes the opposite direction. And the formula for the exponential decay is a little different. Do you remember? How does the formula change for exponential decay? No, becomes e to the negative x, because then it flips it around the y-axis. So a negative up there in front of the exponent flips the graph around the y-axis. If we put a negative in front of the e, what happens? Error? No. What happens to the graph? Flips to the x-axis, I agree. So if a graph that looks like this would be y is equal to negative e to the x. So it's just flipping the one in red. Now be careful here. You might think it's error because what did we say about the base? The base has to be a positive, right, and a constant. If we go back down here, e is 2.7, so the base is positive, right? This negative is just in front of that base. So the base is still positive. How about if we have a graph over here? What would be the equation for this one? Negative e to the negative x. I agree. Because this one is just a flip of the green one above. So all we have to do is put a negative in front of it. Lewis, what do you mean, which one? So this one here that we just drew, right, is a reflection of the one above it around the x-axis. But our basic exponential function is this, which is the one in red. By putting negative signs in there, it changes the graph. Let's talk about this graph some more. Now, what would be helpful here is actually if you have a calculator that is graphing. So let's go back where it's a little cleaner, and we're going to go back. Y is equal to e to the x. And we know this graph looks like this. Now, if we put a number and I don't know what they do using your textbook, but we're just calling that number h. What happens to your graph?
It shifts along the y-axis.
Shifts along the y-axis. So you mean that's a vertical shift?
Yes.
All right. Close, you're on the right track, but it's actually the other way around. So this is a horizontal shift. So this is going to be a left and right direction along the x-axis. But that was very good. Now, if you put a number out here, being added to the overall function, that's the vertical shift. That goes up and down. So this number is a vertical shift. And of course, there are other stuff that's going to change the function, right? But one more thing before we move on. I want to talk about the domain of this function. Does everyone remember domain? What is the domain of a function?
Isn't it positive infinity, negative infinity? I mean, negative infinity, positive infinity.
The positive infinity. I agree. But what is it exactly?
The x-axis?
No, I'm right, the x-axis. It's the x values, right? That satisfies a graph. So if you were to follow this graph anywhere on it, right? If you follow it all the way to the right, the x values keep going up and up and up. It's going in this direction. So the x values are going towards positive infinity. And if you follow it on the left, over here, it continues going over here. So it's going towards negative infinity. So this is why the domain is from negative infinity to positive infinity. All right, what about a range? How high is the graph going up? So the range is a y value. I agree, Martha. So what are the y values that will actually work for this function? Let's write it below where there's more space. How far up does this graph go? So here's our graph. I'm going up in black. If we follow this graph, how high is it going? It's going towards infinity, right? So is it going towards negative infinity? If we follow it all the way to the left, how low is it going? How low is that graph going? Is it going below the x-axis? It's not going below the x-axis, but it's getting closer to the x-axis, right? So what's the y value as we get closer to the x-axis? Not 1, because remember up here the y value was 0 and 1. So that's where y value of 1 is. So that's below 1. So what is the y value along the x-axis? That's correct, right? So the y value is 0. This is 0. This point here is 1, 2. This point is actually 1, 0. This point is 2, 0, right? Because the y values are 0. This point would be 3, 0. So on the x-axis, the y value is 0. So we follow this graph down more to the left. The lowest it's getting, it's getting close to 0. So the range for this function is 0 to infinity. It doesn't go to negative infinity because it doesn't go below the x-axis. And this 0 here, if you recall, we're to draw a line here. This line has a name that it doesn't cross. Does anyone remember? There's that special name for the green line. Line of symmetry? No. It's called a horizontal. The horizontal asymptote. Does that sound familiar now? Let's just look at a couple of questions from your homework on this section. There's only 14 questions on this homework. You have a couple on graphing. So let's just do number 1. Which says f of x is equal to e to the 4x. Now, if you go back up to the top, e to the 4x, to all our graphs, let's number them. This is number 1 over here, number 2, number 3, and number 4. Which graph would e to the 4x look like? Number 1, Jihan Samuel Green. Now look, for the green one, there's a negative in front of the x, right? So be careful. Sam, Red one? Okay, I agree with you now. So the red one or number one, so this graph is going to look like this. So this is a multiple choice question on your homework, right? And it's just going to be like that. You're going to have 4 options and you're going to choose right option. So we know this graph is going to look something like this, right? Does anyone know what a 4 does? The 4 tends to pull it more straight upwards, faster, because you're multiplying the exponent by a number, so it's going to go up very fast. Now, it's not going to move it up or down. It's a stretching of the graph. Up or down is when we have numbers like h and k, a number added to the exponent or a number added to the whole function. That's when it moves up or down, or left and right. But if you have a number multiplying the power, it just means the power is going to be larger, so it grows much faster. Now, this question, apart from asking you which graph it is, they're going to ask us for the domain and the range. So what's their domain for this? Come on, we just talked about this one. Is it the same thing as this graph above here?
Negative infinity to positive infinity.
Yeah, and for all these exponential functions, the domain will never change, okay? Doesn't matter if, look, if you look at, go back to all of them. 1, 2, 3, 4. They're going all the way from left to right. So the domain will always be negative infinity to positive infinity. What's going to change is the range, right? But what's the range for this one? It's identical to the one that we just did. 0 to positive infinity. They also ask us for the y-intercept. What's the y-intercept here? 1. So the y-intercept is 0 for x and 1 for y. I mean, this is... So you have one more problem like that. Let's move on to a problem like this. If it's too small, let me know, okay? I'll just pull it a little bigger. So, can you guys read that now? Can you guys read? Okay. All right, so that's part E. Well, we're going to come back to part E. This is part A, which I didn't copy, right? Let's talk about some of the applications of these exponential functions. One of the main application has to do with compound interest and money. So when you put money in the bank, it grows over time at a certain interest rate. When you put your money, they're going to tell you, whatever the interest rate is. So that's one of the application. So your money over time will grow like this. This is exponential growth. If your money is not looking like that, then you should be investing in something. This is exponential decay. Does anyone know what looks like exponential decay? Any scenario that looks like that? GME. Is that game up, right, Louis? How much is it this morning? I know it dropped about 60% yesterday. But that's not really exponential. Well, I guess it went up exponentially and it came down exponentially, right? That's the current price, $89. All right. I remember a couple days ago it was like 250 something. All right, but so here we have one of the things that looks like this actually is so about a new car, right? This is how the value is over time, right? So when you buy a car right up here at time 0, you know, the value is very high. And the minute you drive it off the parking lot, it takes a big plunge in value. Right? You want a good deal on a car? It's probably better to get a used car because then it has lost a lot of this initial plunge. The price doesn't change as rapidly. Get a 1 or 2-year-old car. What else does this? Exponential decay could be radioactive or radiation. So a lot of radioactive particles exhibit exponential decay in how they break down over time. And this is one of the reasons why they're so dangerous. Because if they continually break down over time, you will follow this graph. It never really goes away. It's just getting closer and closer to 0. Because the range is from infinity to 0. So there's still some amount of radiation left. All right. But let's look at this problem. We're going to come back to do part A first, but we need some formulas to do this. We know the general exponential equation is y is equal to e to the x power. But when it comes to real life, we have a lot of equations that kind of models that. For example, we have a is equal to p times 1 plus r over n to the nt power. See, this is actually our base, which is raised to the exponent here. And this is just a constant. And this is a formula that we use for compound interest. And there's a few things that we need to talk about. A represents the future value of your money. And P is equal to the present value. So P is the amount of money you're going to invest to get a future amount of A. R is the interest rate. And this should always be in a decimal form. N is the number of times per year. So even though we have an interest rate of maybe 3.9% in this problem, that's the interest rate per year, but you do get interest throughout the year. If you check your statements every month, you'll see the interest on it. So they're calculating interest throughout the year. If we talk about monthly, then N is equal to 12. We talk about quarterly, What would n be equal to for quarterly? Four. How about if you get an interest daily? What would n be equal to? Daily for 1 year, Samara? Think about it. 365, right? And if we talk about semi-annually, that would be twice a year and so on. Only thing we haven't talked about yet is t. T is equal to the time in years. So this is one of the formula that they use for calculating compound interest. And there's also another formula they use to calculate compound interest. And you probably have seen this one. Everything remains the same except, I mean, the variables will all represent the same thing. And E here is the same constant that we talk about. We use this one for continuously compounded. You actually drag this down to the bottom. All right, so give us some room. It says find, part A says find the future value when compounded annually. So if we go back up, which one of the formulas are we using? Are we using formula number 1 or formula number 2? Number 1. The only time we use formula number 2 is when it says continuously compounded or compounding continuously. That's the only time we're going to use formula number 2. So annually is telling us something. It's telling us the n value, right? What's our n value?
12.
12 would be monthly.
Hold on, wait.
You got a doc, right? Right, Lois? Maybe. And you're probably going to get a physical, right?
What was that?
I was asking if you went go to the doctor and get a physical sometimes. But normally that's an annual checkup, right? Samara, you go twice,
Yeah. That makes
right?
sense.
All right, so it's one, when we talk about annually, it's one time for the year, right? So if we know that, it's just now a matter of sticking everything in. We're trying to find the future value. So A is equal to P times 1 plus R over N to the NT. So it's just plugging everything in. Our P is 125,000. 1 plus R. What's our R in this problem?
3.9.
3.9. It's 3.9, but we're going to use 0.039 because we have to use the decimal form.
Okay.
Right, which is just moving a decimal point 2 places to the
Going back to me now.
going back. All right, good. And then we're gonna multiply by n times t at the top. So this is 1 times 7, because it's already in years. So it's just a matter of sticking this in your calculator. Can someone calculate this for me, please? So someone got 133,400.19. Now for money, we normally round to 2 decimal places, okay? Can someone confirm Samuel's answer? $163,387.50. So we have a different answer. So be careful how you're entering into your calculator.
I got Damien's answer too.
Damien, Don, and Damien. All right. So Samuel, be careful how you're entering that answer, the numbers into your calculator. So the consensus seems like it's 163,387.50, which doesn't seem return, right? How much money did you make? You started out with 125,000 and you ended up with 163,000. What's the difference there? $38,000. So if you invested 125,000 at 3.9% for 7 years, you'd have made $38,000, 387 cents and $387.50. Not bad if you have $125,000 to sit down in the bank. All right, let's look at part B. Part B is, I'm not going to do part B or C, but it says find the future value when compounded monthly. So what's the difference between this and part A? N is equal to 12. So that's all we're doing for part B. We're just changing N, right? And doing the calculations over. And part C says find future value when compounded daily. So what's changing here? N is equal to 365. All right, so pretty straightforward. We're just changing N. Let's go part D. Find the future value when compounded continuously. What's changing here? The formula, excellent. Right, so when they say then we have to go to A is equal to P e to the RT. So we're still trying to find A. This was still what, 125,000 was our T. Then we have E and the R. Make sure you put the exponent in parentheses. R was still 0.039. Our time was still 7 years. Yeah, I want to get an answer for this. 164,237 and 53 cents. And compounding continuously should always give you more amount of money than monthly or annually or daily or even by the second. Compounding continuous is almost like infinite number of times per year. All right, let's look at part E above. And part E is what we had here. Part E says find the doubling time. So we find the doubling time. Let's see. What is the amount going to be when we have doubled our money? We double it. We start 125,000. We double our money. How much do we have? $250,000. So here they're actually telling us that the A is equal to $250,000. So we're trying to see how long it takes to double our money. So if we go back to this formula, 250,000 is equal to 125,000 e to the RT. And we know our R is 0.039. T we don't know at this stage because that's what we're trying to find. How long is to double it? So it's just a matter of solving this equation. And I think your textbook get ahead of themselves with this problem. So this is more like the second half of 2.1. So let's kind of run through this. We'll come back to it. We're going to divide by 125,000. So this becomes 2. And this will always be 2 for the doubling time, right? So it's never going to change. Anyone remember how to solve this type of equation? Let me remind you. We're going to take the natural log of both sides, which is why I said the textbook got ahead of itself, because we haven't talked about that yet. And if you take the natural log of the right side, this becomes 0.03 nt. Because the natural log will cancel out this base e here. If we divide 0.039 both sides, we'll get t is equal to the ln of 2 over 0.039. So how long is that approximately? $17 years. So it takes you 17 years to double your money. 3.9, Samir. You sure? $18, which is it, 17 or 18? 18. So let's just change this to 18. It's probably 17 point something. All right, but this is also a good formula for doubling time. So instead of going through all our work again when we find to ask doubling time, it is always just going to be the ln of 2 over the r. That will never change for doubling time.